Hello, my name is Jan Unsleber, and today I will be talking to you about exploring reaction networks with our Chemoton 2.0 software. Reaction networks are those networks in which different chemical compounds are connected via reactions. These networks interconnect how we think about chemistry and how it can be modeled. And importantly for this talk, these networks can also formalize a way in which we may compute information about chemical processes. The science software package that we develop, of which Chemoton is a key part, are exactly designed to explore these reaction networks and store them and analyze them, and in general just. As an example for this presentation, I will be using the Johnson-Corey-Tchaikovsky reaction. I've given here an exemplary set of starting materials and the expected outcome, as well as 3 reasonable alternative sets of products that could arise from the same starting materials. Chemoton now sets up reaction attempts that each use a multi-step algorithm to probe for possible elementary steps. This process starts by colliding the reactants and extracting a transition state gas from the resulting trajectory. Subsequently, the transition state is optimized and the reactive coordinate is used to validate the transition state. This validation has to lead to a new product on the one side of the transition state, and on the other side it has to lead to the starting materials. If this is the case, then this reaction attempt is deemed a success and an elementary step has been discovered. Running this procedure for the Johnson-Corey-Tchaikovsky reaction, even with a computationally inexpensive semi-empirical method, shows that our imagined reactions are all found. The vibrational modes with imaginary frequencies for the transition states of all 4 of them are shown here. But let's dive a bit deeper into the numbers of our little experiment. We have picked 1 conformer for each reagent and then ran roughly 24,000 reaction trials, which led to 3,300 elementary steps that were sorted into 488 unique reactions. So besides our 4 assumed reactions, there were 484 other reactions found. As we can see in the bottom right corner, the statistics on the activation energies show that many of these reactions might be of interest to us as they display low barriers. All of this has been carried out in 350 CPU hours, so it would have been possible on a 16-core machine in less than 24 hours, or on a moderate desktop computer over the course of a weekend. Coming to an end here, I hope that this example has sparked some ideas with you on how you could apply this software in your own research. So if that is the case, I would like to point you to our website or the GitHub repository, or ask you to follow me on Twitter, and I or we will let you know when the software is open sourced. Thanks for your attention.